What else we got going on? Review books are available if you want to purchase one or go in on one with someone else. I'm going to say the majority of the mistakes on the exam were in the multiple choice section. If you are not a multiple choice person by default, unfortunately the final exam is all multiple choice. So you may want to practice your multiple choice skills in terms of like being able to quickly get through them and picking hopefully the right answer, or at least narrowing down the right answer, like 2 options. Student evaluations are currently online. We are sitting as of right this second at 52%. If you can make it to 95% by Monday, I will drop a 3rd quiz. So Monday at class time, so however many hours away from now that is. And in case you've forgotten, your final is a week from Friday. At 8 a.m. I'll see y'all then. Yes? Sort of. You have to email the instructor of that section because they may not physically have room in their classroom for you to take it, depending on who it is and what time you want. So if you see that Chem 109 is being offered at a separate time and you would like to take it at a different time other than Friday, email that instructor and say, do you have space for me to take it with your class? Any other thoughts about any of that? All right. So in that case, let's talk about the last section of Chapter 18, which is electrolytic cells, which are the non-spontaneous reactions that can be made to occur by pushing electrical energy through the system. So if I am non-spontaneous, what should my sign of delta G be? Okay. What should my E0 cell be? Negative. Where should my K be sitting? Greater, less than, equal to 1. Alright, so those all be true for an electrolytic cell. So these cells are called electrolytic cells in that I have to apply energy to get the reaction to go. Right, so in all the previous ones they're spontaneous, so they're giving off energy, so I could use that to do something. These, bless you, I have to apply energy to it to get it to do the reaction that I want to do. Let's see. So this is the process through which you can electroplate objects. So if you've ever been shopping and you see it's like gold plated, well, it means that the object is sitting in a bath of gold ions and they applied energy to it and the gold stuck to the object. And so the gold would be sitting out as its Ag plus or Ag plus 2. And then by applying energy to it, the gold sticks to the earring or to the spoon or whatever you're trying to gold plate. Alright, so if I'm going to apply energy, I need to know how much energy and for how long should I apply that energy. That makes sense, because otherwise you're wasting your time and your money. And so, right, you're wasting the time of the workers, you're wasting the time of everybody by not knowing that. So, this energy, in this case, right, is going to be voltage. So I want to know, over here. Alright, so you're going to want to know how much metal is needed, the minimum amount. How much metal will stick to the object. Alright, how much energy is needed and how long the process will take. Alright, so when we normally talk about energy, what units do I typically talk about in terms of energy? Joules. Well, this is a handy-dandy conversion. 1 joule is 1 Coulomb multiplication volt, 1 Coulomb volt. We've talked about volts, right? Volts is voltage. We haven't talked about coulombs yet, specifically. Alright, so C stands for Coulomb. So when I have 1 mole of electrons, I measure that in coulombs. So 1 mole of electrons is equal to a coulomb, which is numerically equal to 9.648 times 10 to the 4th. Here it is, yeah. Yeah, it is Faraday's constant, which is how we get Faraday's constant. It's a mole of electrons. Fun fact. Before we were just using it because it's a constant. But it's a measurement of how much charge a mole of electrons has. Alright, so coulombs, volts, joules. The other thing, right, so that takes how much, oh, how long will this process take? I'm looking for some sort of rate. Alright, how long does it take? Will be in some sort of time measurement, which is amps. Alright, so 1A, A stands for amps. Is the rate of current flow. And it's measured in coulombs per second. So how much charge is passed how quickly. Alright, so now I know about energy, I know about how many electrons, I know about a rate. We're ready to do some unit conversions. Bring it full circle. This whole last section is just unit conversions. Units, 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 units. Alright, so let's say, what's my practice question? I got 2. Okay, that's good. Chromium can be electroplated onto other surfaces. Using that reaction. The question is, using a current of 8 amps and 3.5 volts, how many grams of chromium can be plated if I let the reaction go for 1 hour? Alright, so let's think through what it's asking. Okay. Alright, So there's going to be a process by which we answer all these styles of questions. All right. Alright, so we're going to use the unit conversions. I think you can start it anywhere, but I'm going to start with the 8 amps. Okay. So if I start with 8 amps, what did I say an amp is equal to? Coulombs per second. Alright, what information do I know about time from this question? I know it's run for an hour. Does anyone off the top of their head know how many seconds are in an hour? Alright, so now I'm in coulombs, and I want to get all the way over to grams. Alright, a coulomb, alright, we said a few minutes ago, so 1 mole of electrons is equal to that many coulombs. Why do I want to be in moles? What units do I want to end up in? Grams. The only way we know to get to grams is through moles. Alright. Now I'm in units of moles of electrons. How many electrons are needed to do this half reaction? 12 electrons, right? Based on my half reaction, I need 12. If I put in 12 electrons, how many, I guess, what's the thing I'm interested in the other half, the chromium or the water? So if I put in 12 electrons, how many moles of chromium do I get? 2. So I get 2 moles of chromium for every 12 electrons. What piece of information have I not given you that you need to complete the question? The molecular weight of chromium, which happens to be 52. Alright, so everyone double check my math. Pretty confident on this one, but so if I let it run for an hour, I get 2.59 grams of chromium stuck to whatever thing I'm sticking it to. Turns out bolt's not a useful thing in this case. You just have to run it at a potential that's high enough to overcome the fact that this is not a likely reaction. Right, so it's going to depend on what the other half of the reaction is to make sure you apply enough voltage to get it to go forward. Alright, let's do the other practice problem then. You have a question first? Okay. which is numerically equal to Faraday's constant of Coulomb. Oh, no. 1 mole of electrons have that many coulombs of charge. A coulomb is a measure of the charge of a mole of electrons. I guess, let me rephrase that. Yeah. It doesn't matter at all what voltage it is, as long as it's higher to make it go forward. So the charge of 1 mole of electrons is a coulomb, which is numerically equal to this value. Yes. So if you have a mole of electrons, you add up all the charge, it's going to be equal to Faraday's constant. Thank you. Oh. Alright, here's the tricky one. Alright, so let's say you have your baby spoon that you want to gold plate because you got some spare time and extra cash, right? And you really want to make a silver plated baby spoon. Because why not? Alright, so you have a baby spoon with that given area, and it's plated from silver fluoride for using 2 amps for 2 1/4 hours at a current efficiency of 82%. How many grams of silver were applied? Let's think through what it's asking, right? Alright, so we have this silver fluoride. An electron makes a silver solid, right, which is right, that's the thing we care about. That's the one that's electroplating onto the spoon. What's happening to that chloride ion? Nothing. It's hanging out. What do we call those guys when they just hang out and watch? Spectators. It's a spectator ion in this case. It's not a useful part of the reaction. So we're going to walk through the same kind of idea. So again, we're going to start with our amp. Alright, convert our amps to coulombs per second. What do I know about time in this case? It's 2 1/4 hours. So how many minutes is in 2 1/4 hours? You think about it. Alright, 16, 16, 15. Yeah, 1:35. Oh, question first. I have to do it in seconds, so we're thinking out loud. Right, so 2 1/4 hours would be 135 minutes times 60. Yep. I didn't want to write down 8,100 seconds without thinking through where that random number come from. When you look at your notes later, you'll be like, there's no seconds in the question. Okay. Alright, now I'm in coulombs. So again, I'm going to use my mole of charge of electrons. Alright, in this case, how many moles of electron do I need to make silver? 1, right? And if I put in a mole of electrons, how many moles of silver do I get out? Alright, then what do I need? The molar mass of silver, which is 107.9. Alright, we are almost done, right? If I answered the question right here, what efficiency would I be at? 100%. So how do I figure out what only 82% of that would be? Right, so that takes into account that if I was at 100%, I would get closer to like 20 grams, but because it's not running at full efficiency, I'm going to get less than 20 grams. I think I get like to 16. Alright, that's all there is this last section. It's just unit conversions, and they're pretty much always in the same format. The only other thing that they could ask you is somehow do it backwards. Like, if you want 15 grams of silver, how many amps did you have to apply? So you just work the question backwards. And since, like, a third of you guys have already done the homework for tonight, you guys have already figured this out, maybe. So. Alright, thoughts on that? Questions on that last little bit? Alright, in that case, let's start the last chapter of Gen Chem. Oh, no cheering. No, I don't think that. I'm assuming that wasn't cheering. That was actually sadness. I'm assuming that was an out loud wail. Definitely not cheering. Unless maybe organic chemistry is really your thing. Yay. That's right, that's right. How many people are going on to take organic next? Taking organic, just out of curiosity. Okay, how many people are going on to take analytical next? Taking analytical. How many people are taking analytical next fall? A few, smattering? Okay. I'm just curious, just taking a poll. Are you taking organic? Yes? No. That's it. Has no bearing on the test or anything. I was just curious. That's it. Just curiosity, flat out. Alright, so this last section is nuclear chemistry. And it deals with different types of decay that atoms can undergo and their half-lives. Remember when we did half-lives? They're coming back. Alright. Alright, so radioactivity was discovered as a thing in 1896 by Becquerel, which was then which he's not the famous one, right? Everybody knows about Marie Curie and her partner Rutherford. Alright, so these scientists together found that certain nuclei are unstable. And will spontaneously decompose. So this process of degradation and emission all together is the area of radioactivity. The air conditioning guy was supposed to come by my house. My husband's waiting on him, and apparently he's angry. Apparently he's very angry at figure that out later. Alright, so there are 4 different types of radioactivity that an atom can undergo. Alpha decay, symbolized by the alpha. Beta decay, which looks like a bee, but it has like a long tail. The Incredible Hulk version of it, gamma ray emission. For like the 3 people who know what the Incredible Hulk is and know how he became such, gamma rays. We'll talk about why that's scientifically ridiculous here in a little bit. Totally ridiculous. Gamma rays pass right through you and they don't have enough energy to change your nuclei. But we'll get there. We'll get there. If he was like beta decay, then it could have been a big deal. And the last one's called positron emission. It doesn't have a cool symbol. Sorry. I could totally make one. Maybe we'll think about that. We'll brainstorm what a cool symbol would be. Whatever Greek letters left over, right, that people don't use. Alright, so before we talk about different types of emissions and decays, let's go back and talk about how do I know how many electrons are in an atom and how many protons and all, just basic, just double checking. I'm sure you know this, but just in case. It's not coming to you off the top of your head. Right? Here's my element. The mass number tells me protons and neutrons. The atomic number tells me what? Just protons. So let's say I have these 2 elements. Right, here's neon. How many protons does neon have? Good. How many neutrons does it have? Okay. How would I go about figuring how many electrons it has, assuming neutral charge? Should be equal to the protons, assuming they were at neutral, whatever. Alright, so if I just have regular old neon. Alright, what if I go over here to polonium, one of our crazier elements? How many protons does polonium have? Anyone quick with their math and figure out how many neutrons? 128. And assuming everything's neutral, right, you'd have 84 electrons. Alright, good. Alright, because it's onerous to write down the word proton, neutron, and electron every single time, we do have cool symbols for that. Okay, apparently that's not appealing. Alright. What would that be a symbol for? Hydrogen, could be hydrogen. Or what would the P stand for? It is hydrogen. But P stands for, okay, proton. Proton stands for proton, right? If it has atomic number 1, how many protons does it have? 1. What would its mass number be? 1. It is. This is a proton. A proton is 1 proton. Okay. Yes, for a proton, it's usually symbol 11P. Okay. What should that be? A neutron, right? Why does it have 0 as its atomic number? There's no protons, right? But it has a mass. Okay. What's that crazy guy? The electron. Why does it have 0 mass? Right, because it doesn't have any protons and neutrons, but it has an atomic number of -1, indicating that actually it's down 1 proton. It's not 0, it's less than 0. It's telling you it has a charge. Okay, so we're going to use those symbols to talk about these different types of decay. Alright, so alpha decay, I feel like this angle today is like really weird. Throw me off. Is that more straight or less straight? Like this angle is bothering me. Yeah. A little better. Alright. So alpha decay occurs when you have 2 unstable nuclei emitting a particle composed of 2 protons and 2 neutrons. So 2 protons and 2 neutrons. What should its atomic weight be? Atomic number. No, let me get it. Let's do mass number. What's its mass number? Alright. And then its atomic number, 2. What other element do we know that has a mass of 4 and 2 protons? That is the alpha particle. So 1 helium is an alpha particle. Right? That's how you spell like alfalfa. That's not right. Alright, so when you have an alpha particle emitted, alright, so if I emit an alpha particle, I'm emitting 2 protons. Where do the protons live in my element? In the nucleus. I have now kicked 2 protons out of the nucleus. What have I now done to this element? It's now a new element. Alright, because the element's based on number of protons. Now down 2 protons, at least. It is now a new element. Alright, so let's do one of these. Alright, so let's say I have uranium-238. And it's going to emit a helium. And then how do I figure out what the other thing is? You do subtract. So if I was at 238 and I've emitted 4, what should my new mass number be? If I was at 92 and I emitted 2 protons, what's my new atomic number? How would I look to the periodic table to figure out what element that is? Is it based on the mass or the atomic number? Atomic number, you look up number 80, which happens to be thorium. That is 90, element 90. You had your periodic table near you. I'm still working on them getting a periodic table. I guess the issue is they don't know what wall to hang it on. Because there's no wall that you guys look at except up here, and so there's no good spot to hang one. And then they're like, well, they should just all have one themselves. I'm like, well, in an ideal world, yes, you always have a calculator and periodic table handy at all times. It doesn't always happen, right? Alright, so this is called a nuclear equation. Let's see if I can calm down this angry set of sex. Yeah, it's just a big right now. My fault. My fault I made you stay at home and wait for the air conditioning to go. If you're looking on YouTube later, I'm sorry.
I'm disrupting my entire class by texting.
Okay, there we go. Alright, so this is a nuclear equation because it refers to the nuclear process, right? The decay of the original element. If we're thinking about family units, which we currently are because I'm texting my family unit, what do you call the adult in a family, typically, compared to the kid? The parent. What of these would be the parent in this case? Uranium. This is the parent nuclide. These are all words that are almost impossible to pronounce and not sound stupid, right? Nuclide sounds like you forgot to say part of it. It's a parent nuclide. And then for some reason, whoever invented this method, there are no sons made by this, there are only daughters. This is, I know, reverse sexist, right? The important thing is the daughter nuclide. Well, this is going to be the alpha particle. It has its own name already. So you have a parent nuclide, the alpha particle in this case, and the daughter nuclide being produced. All right. Questions about alpha decay? Pretty straightforward, right? Okay. Let's do the other one. Let's do some beta decay. Beta decay occurs when an unstable nucleus emits an electron. So a beta particle is really just an electron. I'm saying that an electron is emitted when this process occurs. So if a nucleus is emitting an electron, what's going to be left behind? They usually come as a pair. Proton, you're going to leave behind the proton, right? So the atomic number won't change. It'll just be the charge, kind of, right? So take that back. I don't want to explain it that way. Ignore what I just said. The atomic number will change in that it's going to seem like more protons are there than were originally. I'm not adding protons to the nucleus, but I'm effectively changing the number of protons being felt because it's one less electron. Let's do an equation. Let's look at this. This is not my best lecture, guys. I apologize. Alright, let's say I have radon, 228 radon, and I want to emit a beta particle. What will have changed in my mass number? Nothing. If I have 88 on this side and minus 1 on this side, what has to be the new atomic number? To get things to add up, right? 88 is 89 minus 1. As I'm saying, the atomic number has effectively changed in that I've lost an electron from, we would normally just call it charged, but because I'm specifically doing beta decay, it changes the atomic number. Maybe it's a weird look you guys are all giving me, but I'm just, okay, maybe I'll try another one. Let's try. Maybe that helps. I don't know. The negative means it's an effective number, atomic number of minus 1. Sorry. in that I'm not making an ion specifically. Like, it's going to be charged in that it's down 1 electron. But on the overall scheme, it's going to seem as though it's up 1 proton. Well, right, that's why you have to know it's beta decay. Because beta decay is different than ionizing. Because I'm letting loose an electron. Right, this electron is not going anywhere yet. It's a free electron. The thing I yell at you guys about in electrochemistry, you can't have any free electrons. You can if it's beta decay. I don't know why I put this at the end, because you guys are already so overwhelmed. We should probably do this chapter earlier in the semester. Do you want to see another thing where I add them up? That doesn't seem to make any difference to you. Alright, well, let's do another one. Alright, let's move on. Alright, good enough. Well, let's talk about gamma rays. Alright, so gamma ray emission is a high energy short wavelength electromagnetic radiation. Remembering all the way back to, I think, the second lecture I give in 108, where we talk about electromagnetic radiation. Right, there's radio waves, there's IR, UV, visible light, all those options. This is a high energy source, right, those are opposite. Right, wavelength and frequency are opposite. Right, one, okay. If I tell you that gamma ray is this, what am I telling you about it? What's its charge? What's its mass? Nothing. It's a ray. It's not an object like the last two. The last two is like a physical proton or physical electron. This is just energy. It is not a physical object. So it's no different than when something emits light and you can see it. This is emitting energy. It's just you can't see it because it's in this wavelength that you can't visibly see. Since gamma rays have no mass or charge, they are typically emitted along with another particle. Why would I have to emit another particle to change the element? Right, it doesn't have any protons associated with it, and the number of protons tells you that the element has changed. And so typically you have to do two things together. So if I have what must be the other thing that was emitted? It's one of the first two choices. Yes, an alpha particle. Which makes sense, right? It's the only way it adds back up. It doesn't have to be. It could be a beta particle. But usually what happens is they measure this and they see the new element, and then you kind of figure out what the third thing that happened was to make it add up. Sure, why not? Let's do. And then I'll pass back the exam. So what's the new top number of my element? This, then this is going to be 34, which is selenium. Yeah. Question first. True. Yeah. True. Alright, we'll try it again on Friday. I mean, maybe